Next, we are going to discuss an example of a data flow analysis which involves bounding the range of an integer variable. And I'm going to call it the range analysis. And this is just an example DFA just to review some of the concepts that we have learned so far. So let us say a range analysis basically aims to bound the value that a variable x can take within a range, lower bound and upper bound. And let's say in my example, I'll just take one of those bounds and let me just take the lower bound. So I'm interested in what is the minimum integer value of a variable x that a variable x can take. Now, when I want to design a DFA for something like this, it's the first question that comes to mind is what should be the direction of the DFA. Now, because we are interested in the minimum value that integer x can take at any program point, the value that a variable takes at a program point depends on the assignments that happen before it. In other words, the information needs to flow forward in the direction of program execution, and for that reason, the direction of this DFA is forward. The next question we want to ask is what is the domain of values? And in this case, the lower bound could be as small as the minimum representable integer in your language. Let me call that int min. And then all the other integers like minus 3, 4, minus 2, minus 1, and then all the positive integers 1, 2, and all the way to the maximum possible representable integer. Let me call that int max. Now, although I'm using int min and int max, later I'm going to actually just coarsen this analysis, and just for kind of ease of exposition, I'm just going to use minus infinity for int min and plus infinity for int max. Now, in general, it is not it's not a right thing to actually use minus infinity and plus infinity in a programming language. All programming languages basically bound the set of representable values because they are after all finite, whereas the set of mathematical integers are actually infinite from minus infinity to infinity. But just for our analysis, let's just assume that our programming language supports mathematical integers, and so the values that a variable x and of type integer can take are from minus infinity all the way to plus infinity. So the next question that comes forth is basically what is the meet operator for my DFA. And to answer this question, I want to basically ask the question that at any program point, if a value v1 is flowing from one branch and a value v2, lower bound v2 is flowing from another branch for the same value x, for variable x. So v1 is the lower bound on x from one branch and v2 is the lower bound on x on another branch, then what can we say about the lower bound of x at the meet point? And the answer is we want to be accurate. We want to be conservatively accurate in the sense that we want a real lower bound. So in this case, the lower bound is going to be the minimum of v1 and v2, where min is the integer minimum operator. So the meet operator is minimum of two values. For example, the meet of minus 1 and minus 2 is minus 2. Okay, so using this meet operator, I can now construct a semi-lattice. And in the semi-lattice, the partial order operator that kind of derives from the meet operator is just the integer less than equal to. This is just the integer comparison less than equal to. And if I was to draw this as a graph, then int max is the top value in this semi-lattice. And then, all the positive values in decreasing order, maybe plus 1, 0, and then all the negative values, minus 1, minus 2, and so on, all the way to int min. And you can check for yourself that, actually this is in this semi-lattice, the meet operator is min. In fact, in this example, it so happens that this semi-lattice is actually also a total order, not just a partial order. But one of the things that's interesting about this semi-lattice is it's a very, very, very long height. And in our abstracted world of mathematical integers, it actually has an infinite height. So we're going to see what the implications of that can be. So once again, I'm basically going to assume that int max is plus infinity and int min is minus infinity. And now let's say I have this program which basically initializes at entry the variable x to 10. And then inside the loop body, it says x equals x minus 1. And then it says if x is greater than 0, then go to loop. And so this is a loop. And then when it exits the loop, then it just returns x. Now I want to analyze what are the possible values of x at every program point. Maybe I'm interested in figuring out what are the possible values of x that the program may return. So I'm going to use my data flow analysis, and the first thing I want to do is basically I've already defined the semi-lattice, but I also want to define what the boundary condition for X is at the entry. So what can I assume about the boundary condition? What is the lower bound of X at boundary condition? And let me assume that I don't know anything about what X could be at entry. So in that case, I basically kind of what is the kind of most safest lower bound that you can think of, where you don't know anything about X. That would be just int min, because everything would be greater than equal to int min in my domain of values that X can take, and which we are also assuming is minus infinity, and this is also the bottom value of our semi-lattice. So the boundary condition for X at entry is just that it is minus infinity or bottom. But when we initialize the interior points of our DFA, recall that we initialize them optimistically to the top value of the semi-lattice, because as the DFA progresses, the values just become lesser and lesser. So initialization at all the interior points will be to the top value, which in this case is int max or plus infinity. Okay. Now, before I start executing the DFA on that particular example, I also need to define some transfer functions for the statements that appear in that example. So first of all, if I have a statement which says x colon equals some constant c, then whatever value is flowing in, I can be sure that at the out, the lower bound of x is actually c, because I am sure that x will be equal to c. So out is just c in this example. Similarly, if I'm doing some arithmetic on x, such as x colon equals x plus minus c, then if in is some value that's flowing in, so let's say in is the value flowing in from in is in, then out is just in plus minus c. So for example, if in was 2, then out is 2 plus minus c. So if c was, if it was, if this instruction was x colon equals x plus 1, and if in was 2, then out is 3. That's what this means. And finally, I have in my loop operator, I had this conditional branch, which I'm representing as this if statement. So if x is greater than some constant, go to some label. In this case, there are actually two transfer functions that I should define ideally. For the same value, that for an input value that's flowing in, which is the lower bound of x, there may be one, I may want to use different values for the outputs depending on which output I'm looking at, whether I'm going to the label or whether I'm going to the fall through branch. So either I'm going to go to the label, in which case, what should be the out value at the label, or I'm going to fall through, which means I'm not going to the label, which I'm going to the next instruction, in which case I'm going to get the out fall through. And what can I say about the transfer functions for both these branches? Well, maybe I want to say that out label, because nothing is changing, it's just, it's just branching, it's just a control flow structure, it's not changing the value of x. So maybe I want to say that out label is just in and out fall through is also just in. So the value just gets transferred. So whatever was the lower bound before this instruction is also the lower bound after this instruction on both the branches. Now with these transfer functions, let's start running our DFA on this example program that I showed you earlier. And recall that we initialize the value at the entry with the boundary condition, which is int min. But I initialize all the other interior points with the top value, which is int max. Now, I run my work list algorithm and I figure out that this point here is basically violating my DFA constraints. And so I transfer values, right? So I transfer the value, and because at entry it was int min and nothing has changed, it's just a no op instruction. So int min should also belong. So this value also becomes int min. Now the next time this value gets transferred across the statement x colon equals 10, and recall that the transfer function for x colon equals c was just the output would be c. And so in this case, the next step, the value becomes 10 at the end of this particular statement. And this is the lower bound of x at this point, as we have identified it so far. Now I continue this analysis, and now I'm going to look at this point, and this point has two predecessors. One is this point where the value is 10, and the other is the loop point, where the value is int max. And the recall that the meet operator is the minimum of the two values. So the value that I get assigned here is minimum of 10 and int max, which should be 10 again. Okay. Now, once again, I transfer across x colon equals x minus 1, and now I use my second transfer function, which is going to decrement 10 by 1. And so the value that comes here is now 9. Similarly, the value that flows to the next instruction here across this edge is just 9. And now I have this conditional branch instruction, and we recall that the conditional branch was also just transferring the values across both its branches. So on both the branches, the one that's going back to the loop label and one that's falling through to the return statement, the value of x becomes 9. Are we done yet? Let's check. Well, indeed, if I look at this point, then the value here is 10. But if I look at its predecessors, one of the predecessors is 10, but the other predecessor is now 9. And so this, I need to kind of meet 9 with 10 and recall that the meet operator is minimum. So this 10 becomes 9. And so now this is the new state of my DFA. And once again, because of x colon equals x minus 1, here 9 becomes 8. That flows all the way throughout the loop. And the new state of the DFA becomes 10, 9, 8, 8, 8, 8. Now, once again, the value 8 will flow back into the loop and you will do a meet, and minimum of 9 and 8 will be 8. And so we get 8, 7, 7, 7, 7. And this will keep going on for another 9 or 10 iterations until we get 2 at the loop head, and we have 1, 1, 1, 1 everywhere else. Now, it's still not a stable state. If I need to transfer the value 1 on this loop edge again and take a meet with 10. And so meet of 1 with 10 is actually 1. So this 2 should now be changed to 1. And now I'm at 1, 1, 1, 1, 1. And now because 1 is here, then we again transfer it. It becomes 0 and 0 and so on, and becomes all 1 and all zeros. And then once again, 0 flows back, and then min of 10 and 0 is 0. So the loop head becomes 0, and all the other values in the loop become minus 1. And similarly, minus 1 and everything else becomes minus 2. And this keeps going on until all the values become minus infinity, right? So, we can clearly see that there's a problem with this DFA. And the problem is, first of all, it takes an infinite number of iterations or steps to converge, because I just kind of keep decrementing the value of x by 1 each time, and a number of values that x can take goes all the way till minus infinity from let's say 10 or something, and this is not acceptable, because our DFA algorithm should terminate within a bounded time. Moreover, this is not a useful answer that we got, because saying that the value of x at the return point is just minus infinity, or the lower bound on the value on x is minus infinity, is actually conveying no information whatsoever, because you already know that minus infinity is the lower bound on all possible integers that our language can represent. And so that's not a very useful answer. So not only do we take an infinite number of steps to converge, but we also don't get a useful answer. Now, why did this happen? Well, as we have already discussed, this happens because the fact that it takes infinite number of steps to converge, the running time is not bounded, is coming from the fact that the semi-lattice height is not bounded, and semi-lattice height is infinity. Now, I want to point out that although the analysis that I showed you earlier was going to take an infinite number of steps, the choice of the transfer function often makes a difference in the precision of the analysis, and sometimes even on the running time of the analysis. So let's say I just chose a more precise transfer function for the conditional branch. All of the transfer functions remain the same, but for this conditional branch, I chose different transfer functions for the loop edge, which is out label, and the fall through edge, which is out fall through. So for the out label, let's say I use the fact that I go to label only if x is greater than c. So that means x should be at least c plus 1 if I go to label. So if I look at the loop branch, then out label should be, it could be in, or if in was greater than c, then the best thing I can say about out label is that it could be in, because nothing has changed. But if in was less than c, then I wouldn't have gone to label, right? So the only reason I would have gone to label if x was greater than equal to c plus 1 or c plus 2 or something like that. So if I have gone to label, then I know that the value must be greater than equal to c plus 1. And so from that, I can say a more precise transfer function could be that out label is maximum of n comma c plus 1. Similarly, I can define a more precise transfer function for the fall through branch. For the fall through branch, I know that if n was greater than c, then I would never, that basically means that x must be, because I know that n is the lower bound of x, and I know that n is greater, if I know that I see that n is greater than c, then I know that x must be always greater than c. And for that reason, I know that this branch will never go to the fall through. So if n is greater than c, then I can just say that, look, because it will never go to out fall through, I can just take, make the more precise answer, give the more precise answer, the maximum value, the minimum value that x can take is int max, because, or int plus infinity. In other words, that's like saying that the program will never reach there. It will never come to outfall through, because so far in our analysis, we have identified that the lowest value that x can take, which is in, is always greater than c. So if the lowest value that x can take is greater than c in our analysis so far, then I can just use int max for the value that at the transfer function of outfall through. However, if n was less than equal to c, then I could use the in value, just like I was doing earlier. Now these two transfer functions are more precise than the transfer functions that I used previously, because in the previous transfer functions, recall that I was just using in both situations. But now in the new transfer functions, I may return values that are larger than n. For example, I could return max of n comma c plus 1, which is guaranteed to be larger than n, or I could either return in or int max, which are both guaranteed to be greater than equal to n, right? Same in both sides. So in other words, I'm returning better answers or more precise answers. I'm being able to compute a better lower bound or a more precise lower bound. I'm conveying more information in my transfer function. Now with this transfer function, let's try to run our DFA once again. And once again, we initialize our values to int min at the boundary and int max everywhere else in the program. Now recall that eventually this, one of the states that we got in our DFA was that this becomes int min, and then this becomes 10 to, this becomes 10 by the virtue of this assignment x colon equals 10. But then, slowly the values keep counting down, and we eventually get to 2, 1, 1, 1 here. Now, although the transfer function of the conditional branch is slightly different in this new setting, you can check for yourself that actually this still goes from, it still kind of counts down from 10 to 9 to 8 all the way till 2 and then 1, 1, 1. But one of the things that is good about this analysis, because of the more precise transfer functions, is that so far I have identified that I'll never get out of the loop. And that's why the value that I have for the return edge here is int max, because if the minimum value that x can take is 1, as my analysis has figured out so far, I know that this loop will always be taken, or this loop edge will always be taken, and the return edge will never be taken. And for that reason, I can use the best possible answer that I can use here is int max for the lower bound of x. But this is still not a fixed point solution, because if I look at this point here, then its predecessors are, one of them is 1 and the other one is 10, and the meet of 10 and 1 is 1, whereas the value that I have here is 2. So the next thing I need to do is change this value to 1, and everything else remains same. So 1, 1, 1 and int max. And now this 1 gets transferred across the x minus 1 and becomes a 0. And this 0 just gets transferred to another 0 just before the conditional branch. And now we need to apply the more precise transfer functions of the conditional branch. And recall that on the loop edge, the transfer function was max of in, which is 0, and c plus 1. So c here is 0, so c plus 1 is 1. So the value that gets transferred on the loop edge is going to be max of 0 comma 0 plus 1, which is 1. And the value that will get transferred on the return edge or the fall through edge would be if in is greater than c, then int max. Otherwise, in, but it is not greater than c, right? 0 is not greater than 0. 0 is equal to 0. So I'm not going to transfer in int max this time. Instead, the value that gets transferred outside is the same value that came in, which is 0. So this will be 1 and this will be 0. So this will be the new values after I use the more precise transfer functions. And so this becomes 1 and this becomes 0. So on the loop edge, I am getting the value, the lower bound as 1, which is coming from max of n comma c plus 1, n being 0 and 0, c being 0 as well. And on the return edge, I'm getting 0 because I'm using this transfer function. If n is greater than c, then int max else n. And recall that n is 0 and c is 0 also. And wow, the interesting thing is this is actually a fixed point solution, and we have reached the fixed point. You can check for yourself. For example, if you look at the loop head, then the value that I have here is 1. And if I look at its predecessors, one of the predecessors is 10 and the other predecessor is 1. Right? So, so in this case, I have reached a fixed point solution in a bounded number of steps for this particular example, even though I had an infinite height lattice. What this tells us is that more precise transfer functions can yield more precise answers, and also it tells us that it's not necessary that if the semi-lattice is infinite height or unbounded height, then the fixed point solution must run forever. In some fortunate settings or lucky settings, we may have situations where the fixed point actually terminates. But you know, we don't know what the program is ahead of time. So I can always construct a program in which the fixed point solution can take in infinite steps if my semi-lattice was infinite height. So in general, it's a very bad idea to have a semi-lattice of unbounded height because you don't know what the program is going to be. For example, if I just change this program such that, you know, instead of this if x greater than 0, if I had some other variable y, and then y was basically some function of x, which was, you know, which was some complicated function, but which was actually going to be return a Boolean value that was equivalent to x is greater than 0. Our compiler analysis will not be able to, you know, look into this complex function f and say that, hey, this is actually x greater than 0, in which case also, even with the more precise transfer functions, I'm going to still end up with infinite number of steps in my fixed point solution or algorithm, and I'm going to end up with a very imprecise solution. So to conclude, a more sophisticated transfer function may yield more precise answers, but it's not a guarantee. It is always, in general, it is always possible to construct a program where the DFA yields an imprecise answer. So if you give me any DFA, recall that the transfer functions of a DFA are usually based on pattern matching, you know, pattern matching on the structure of the instruction and so on. And if I, you know, create a program which has the same effect but does not match the patterns that the transfer function uses, then I will, you know, I will be able to create a program in which the DFA will yield imprecise answers, as we saw in the example that we just saw. And in general, we should always ensure a bounded height semi-lattice so that even though the answers are imprecise, the running time of the algorithm is bounded, because this has to run within the context of a particular program analysis or in the context of a compiler, and we cannot wait for a compiler to run forever or for a very long time.